Thank you, Jane. Thank you all for coming to this lecture today. And I'm delighted to be contributing to this joint meeting between Gresham and the British Society for the History of Mathematics. And my part in this series of talks is that I'm going to talk about the square root of -1, now usually denoted by the letter I. And clearly, when you square any number, you can never get a negative result. So what could possibly be meant by the square root of -1? It's no wonder that it was called imaginary, and it took centuries for it to be accepted. I will discuss why the square root of -1 arose in mathematics, how it was represented, and how it was all eventually demystified by the 19th century Irish mathematician William Rowan Hamilton. As well as Hamilton's work on imaginary numbers, he also discovered or created quaternions, a non-commutative algebraic system, and this work helped free algebra from the constraints of arithmetic. So, what could the square root of -1 mean, since every real number, positive or negative, gives a positive result when squared? So the square root of -1 cannot be a real number. And Euler, for example, in the 18th century, who worked with this type of number a great deal, also said, "Of such numbers we may truly assert that they are neither nothing, nor greater than nothing, nor less than nothing, which necessarily constitutes them imaginary or impossible." And in the next century, in the early 19th century, there was still a great deal of unhappiness about so-called imaginary numbers that didn't seem to exist. For example, Augustus de Morgan, Professor of Mathematics at University College London, declared that "we have shown that the symbol square root of -1 to be void of meaning, or rather self-contradictory and absurd." But however strange imaginary numbers seemed, they were of great use, for example, in solving quadratic and other equations and in other areas of mathematics. So in the next couple of slides, I just want to set up some notation, first of all, that if we allow the square root of -1, then we can form many more numbers of the form, such as 2 plus 3i, 3 times the square root of -1, or 4 plus 5 times the square root of -1, and they're called complex numbers. And suppose we try to calculate with them. Well, we can add them very easily. Here we've got an example, which I hope is correct. 2 plus 3. When you're doing this type of thing, you spend more time trying to get the formatting right, and sometimes the actual numbers don't add up. But you see what's happening there. You're adding up the 2 with the 4, the 3 times the square root of -1 to the 5 times the square root of -1. And multiplication is also easy if we try to multiply those two complex numbers, as long as every time you meet the square root of -1 multiplied by the square root of -1, you replace it by -1. Then it's just the arithmetic we know and love. You multiply every term in the first bracket by every term in the second bracket, and then collect them together. And whenever you have the square root of -1 times the square root of -1, you replace it by -1. And hopefully that is correct, giving you that particular answer. So you can carry out all the standard operations of arithmetic on these new objects. And then the next slide just establishes some terms. As I say, we call the object a plus b times square root of -1 a complex number. The number a is its real part, and the number b its imaginary part. And nowadays we usually follow Euler, who used the letter I, the first letter of imaginary, to mean the square root of -1, so that I squared equals -1. So complex number usually written a plus bi, where I squared is -1. If b equals 0, we get the real number a. And if a equals 0, we get the imaginary number b times I. Okay, so possibly the first time that many people meet complex numbers is when they come to solving quadratic equations. And examples of quadratic equations are x squared minus 6x plus 8 equal to 0. And that can be factorized as x minus 2 times x minus 4. So it's got two real solutions, x equal to 2 and x equal to 4. But if we modify the equation slightly, x squared minus 6x plus 9 equal to 0, then you can factorize that as x minus 3 times x minus 3. And there's a repeated real root there of x equals 3. A slight modification again, x squared minus 6x plus 10 equal to 0. But if we're going to factorize that, we need to bring in I, the square root of minus 1, and then you can write x squared minus 6x plus 10. You can write it as x minus 3 minus I multiplied by x minus 3 plus I. So there are two complex roots there, 3 plus I and 3 minus I. And we can get an idea of what's going on. I think it's helpful if you do the graphs of these three quadratic equations. The one on the lower one was the first one, which had two real roots. The one in the middle is the one that had the repeated real root, and the one at the top is the one that has the two complex roots. Right. So we're going to look and see what happens if we try to solve higher degree polynomials. For example, just wanted to say, because we'll need it in a little while, and indeed the formula for solving a quadratic equation shows us that all we need are complex numbers in order to solve quadratic equations. So that's the point I want to develop. All we need in order to solve quadratic equations are real numbers and complex numbers. So the question I'm going on then to ask is, what happens if we look at higher degree equations? So for example, if we look at this higher degree polynomial, which is of degree 6, can this only be solved, or can this be solved using only real and complex numbers? Or do we need to introduce another type of number? And there are various scenarios that could happen. We only need real and complex numbers. We need to introduce new hypercomplex numbers. Some equations have solutions which are not numbers. Some equations have no solutions. So let's see what happens in a simpler example. We know that real and complex numbers are enough to do quadratics. Let's go one step up and let's try cubics. Let's try a particular cubic. Let's try the cubic equation x cubed equal to I, or x cubed minus I equal to 0. So we're trying the cubic equation x cubed equal to I, which should all be in the one line, or x cubed minus I is equal to 0, and try to see if complex numbers are sufficient. Turns out that they are. And we see that relatively quickly because it's possible to find one solution of that equation because it's so straightforward. You can find the solution just by inspection. And there's one solution which is x equal to minus I. That is because if you cube minus I, there we have it there, this is the laser, minus I times minus I times minus I gives you I. Remember, I squared is minus 1. All right? So now, since we have one solution of the equation, we're able to factorize the equation. X cubed minus I can be written as x plus the root, x minus the root we have, so that's x plus I. And the remaining term is x squared minus ix minus 1. But remember what I said to you, we know we have a formula for solving quadratics, so we can apply that formula to this quadratic term here, and we obtain the other two solutions of the original equation. So we obtain our three solutions as minus I and a half into root 3 plus I and a half into minus root 3 plus I. The point to take away from that is that it turns out that real numbers and complex numbers are enough to solve that particular cubic. And now if I go to the example I had a moment ago, which was this degree 6 equation here, you can apply a similar kind of technique because one's able to factorize it as a product of these three quadratic expressions, and then you are able to factorize each of these quadratic expressions using either real numbers or complex numbers. So this degree 6 equation can also be solved only using real and complex numbers. And there's a very, very important result called the fundamental theorem of algebra, which tells you that that is true for all. The fundamental theorem of algebra tells us that's true for every polynomial equation, so that we don't have to introduce any new hypercomplex numbers, any new type of number, in order to solve any polynomial equation. Every polynomial equation of degree n, various ways of stating the result, has exactly n real or complex roots. As long as you count them appropriately, that's taking account of repeated roots. All right. So to go on to the next set of polynomials I want to look at, it'll be convenient to look at a particular way of representing complex numbers, and that's representing them geometrically. And towards the end of the 18th century, complex numbers were given a geometrical form by the Norwegian-Danish surveyor Caspar Wessel. And in this representation, called the complex plane, which many of you may be familiar with, you have a real axis going horizontally, an imaginary axis going vertically, and if you have a particular complex number, such as 4 plus 5 times I, 4 plus 5 times the square root of -1, it's represented by a point of 0 size, going 4 in this direction, the real part of it, and 5 up in that in the imaginary direction. Now, the advantage of this is that it allows us to represent complex numbers in another way using polar coordinates. And here we have the polar form of a complex number. And again, we have our complex number up here, a plus ib, meaning that we've moved a distance a along the horizontal axis and a distance b up the vertical axis. But if we now look at this triangle with one vertex at the origin, the other one at the complex number, and the vertical line here and the horizontal line here, looking at that triangle and denoting the angle which the line joining the origin to the complex number makes with the positive real axis, calling that theta, then we get that the distance a is going to be r cos theta, where r is the distance that the complex number is away from the origin, and the imaginary part here is going to be r sine theta. So that means that the complex number a plus bi can be written out as r cos theta plus I r sine theta. And we have here, yes, and we use the notation r theta for these polar coordinates of the complex number a plus bi. Now, the advantage of this polar representation is it makes multiplying complex numbers, once you can write them in polar form, very straightforward. So that here we have two numbers, multiplying two numbers in polar form. So this is one complex number, so this means that this complex number is a distance r away from the origin, and the line joining it to the origin makes an angle theta with the positive axis. This is a complex number which is a distance s away from the origin, and the line joining it to the origin makes an angle phi with the positive real axis. And if you multiply the two together, the result is the complex number which is a distance rs away from the origin, and the line joining the answer to the origin makes an angle of theta plus phi. So multiplying two complex numbers when they're given in polar form is very straightforward. You just have to multiply the modulus here and add the corresponding angles. The proof of it is just a matter of following it through, how one multiplies the two numbers together, gathering up the terms, and you see that the first term here, the real term, is cosine theta, cosine phi minus sine theta, sine phi, and then you dig back into your memory or whatever, and you recognize those as the addition formula for the cosine and the sine. And just give you an example here as to what this means geometrically. What I'm going to do is to multiply a complex number 3 plus 2i. I'm going to multiply it by the complex number I. Well, the complex number I, written in polar form, it's one distance, the complex number I is 1 unit away from the origin, and the angle that it's making is 90 degrees, pi over 2. So when we multiply 3 plus 2i by the complex number I, we have to, its distance away from the origin stays the same, because it's the number 1 here, and the angle changes by adding on pi over 2, so it rotates by 90 degrees. So multiplying 3 plus 2i by I rotates it by 90 degrees anti-clockwise. So that was such fun, let's do it again. So let's multiply a complex number by I twice. Well, the first one rotates it by 90 degrees, which was the one over here, and the second one, the second multiplication by I, rotates it by another 90 degrees. So the answer is Starting off with 3 plus 2i, you end up with minus 3 minus 2i, which is what you would expect, because what is multiplying by I twice? That's I squared, and we know I squared is minus 1. So let me then use that to help us to solve some more polynomial equations. And to do that, I want to introduce the walrus theorem here. And this is telling us, in the same way that we had the addition formula before, that if you raise the complex number cosine theta plus I sine theta to the power of n, the answer is the complex number cosine n theta plus I sine n theta. And if you think of the formula that I had back here, you see it's just a continued application of that. It's one way of viewing it. All right. So let's put that together with the fundamental theorem of algebra to try to solve solutions of this equation here, z to the n equal to 1. Solutions of this equation are called roots of unity because any z that satisfies that there when raised to the power of n is going to give you the answer 1. They're called the complex roots of unity. And I'm just going to do it for the case n equals 4. And by the fundamental theorem of algebra, it tells us that we know there are exactly four roots, 4 and only 4 roots to that equation. And I'm going to write down those 4 roots and then check that they give the right answer by using the walrus theorem. So I'm going to write these down, and your exercise, when you finish John Barrow's exercise on the way home, is to work out perhaps how I got these. These are the 4 contenders, I am saying, for the 4 fourth roots of unity. And how do I check that they are? Well, I raise them all to the power of 4. That's me raising them to the power of 4 here. And what do I have to do? Well, I have to multiply the angles in here by 4. And so they're 2 pi over 4 multiplied by 4 gives me the 2 pi. Here, 4 pi over 4 multiplied by 4 gives me 4 pi. So when I raise each of them to the power of 4, I get these 4 numbers over here, each of which is 1. All right? So that means that these numbers here are indeed fourth roots of unity, and when I work out what they are, using what the cosine of 2 pi over 4 is and the sine of 2 pi over 4 is, I get that they are I minus 1 minus I and 1. And we know there could be no other fourth roots. We know there could be no other solution to that equation, z to the 4th equals 1, by the fundamental theorem of algebra. And there's a nice geometric representation of these because these all lie on a circle of radius 1 centered at the origin, and in fact they lay on the vertices of a regular fourgon, usually known as a square. Here we have your 1i minus 1 and minus I. And in fact, if you go to the cube roots of unity, the 6th roots of unity, the same pattern happens. The cube roots of unity lie on an equilateral triangle on a circle of radius 1 about the origin. The 4th roots of unity I've just done here, and the 6th roots of unity lie on a hexagon, which lies on that circle as well. All right. Now, I've been showing you some of the uses of complex numbers. Rowan, in his book, will discuss their origin in the solution of equations, and in particular in the 16th century, the exciting story of how they were used in finding solutions of cubic and quartic equations. But I've been doing quite a lot so far, but I haven't actually told you yet as to what is the square root of minus 1. We'll be following a sort of operational kind of path to it. And it was William Rowan Hamilton who eliminated the confusion and a lot of the mystery, suspicion surrounding them. And Hamilton was born in Dublin in 1805. He achieved international recognition in his own lifetime. He was elected first in the list of foreign associates in the newly formed American National Academy of Sciences, and they were the people considered by the American Academy of Sciences as the most distinguished people working outside America. And Hamilton, he had done world-class work in geometrical optics and also in dynamics, but it was his work in algebra that won him the recognition from the National Academy, and I'll be saying a little bit about that. All right. So he took first place in the entrance examination for Trinity College Dublin, quickly scaled the academic ladder, becoming Professor of Astronomy and Astronomer Royal of Ireland at the age of 22 before he even graduated. So what did he do to resolve the problem of the square root of -1? And in hindsight, especially with what I've said to you about the geometrical representation, it seems very obvious and is now generally accepted. All right. So the question Hamilton had in his mind was, is there any other algebraic representation of complex numbers that reveals all valid operations on them? All right. And what he did was he proposed to define a complex number as a pair of real numbers. Now, if you believe in real numbers, whatever belief is, never mind whatever real numbers are, this is just asking you to believe in two of them. All right? So he's saying a complex number is just a pair of real numbers, a first one and a second one. All right? Now, if he's going to do arithmetic with them, he has to tell you how to add and subtract them. Add, subtract, of course he does, but more importantly, add and multiply them. And addition is the addition that you would have come up with yourself. If you've got two of these pairs, you add them by adding the first member of each pair and adding the second member of each pair. So that's what addition is for these pairs of real numbers. Multiplication, not so obvious. You don't multiply them by multiplying the first element of each pair and the second element of each pair. It's less obvious. It's less obvious. All right. So the rule for multiplying these pairs, now these are just pairs of real numbers, so they're nice and concrete. That's what I'm trying to stress. AB times CD. What you do is you form another pair of real numbers, and you do it by multiplying the AC minus BD. You can see it for yourself. The first number in the first pair by the first number in the second pair. Take away the second number in the first pair by the second number in the second pair. It's quite hard to say that standing up here, you know. And the second number in the second pair, as well, I didn't have that drink at lunchtime, is the second number in the second pair, you can see, is the first in the first pair by the second in the second pair, and the second in the first by the first in the second. Thank you. Thank you. I didn't know there was that many family in today, but there you are. Okay. And you say, that's fine. That's very, very good. You've got pairs of real numbers, and you've got a way of adding them to get another pair of real numbers, a way of multiplying to get another pair of real numbers. What's this got to do with complex numbers? What I say is this exactly parallels what we've been doing with complex numbers, because we can associate the pair A0, it's moved up a little, has it? The pair A0 can be associated with the real number A. So if you just make the second entry in all of these pairs 0, the way that the first entries will combine is just the way that ordinary real numbers multiply. Because if B and D are 0, then B and D are 0 here, so that's naught. So you get A, 0 multiplied by C, 0 is just AC, 0. Right? Just multiplies like ordinary real numbers. But let's look and see what happens. If a number with 0 in the second entry can be thought of just the real number A, let's see what happens when we use this way of multiplying two things together for the pair 0, 1. So let's look at 0, 1 multiplied by 0, 1. Well, there's 0 in the first two entries, so the A and C are 0. So that term is 0. It's not there, John. And you have B and D are both 1, and it's minus BD, so it's minus 1. What's the second entry going to be? Well, we know that B we know that A and C are 0, so the A is 0 there, the C is 0 there. This 0 is very handy to have had that earlier. Excellent lecture. So there's going to be 0 in here. So if you multiply 0, 1 by 0, 1, you get the answer minus 1, 0. And minus 1, 0 we're associating with, minus 1, 0, it just corresponds to the real number minus 1. So one can think of the pair of real numbers, 0, 1, as corresponding to I. It's just disappearing slightly off the bottom of the screen, which corresponds to the equation I times I is minus 1. So this means that you could rewrite anything in complex number theory, variable theory, whatever, using pairs of real numbers. Right? It so happens that the notational convenience of introducing the I is very helpful indeed, but the demystification that happens is that complex numbers are pairs of real numbers with a certain way of adding them and a certain way of multiplying them. Right? So that was the demystification that occurred. So you're now no longer frightened of complex numbers, right? And what I'll do is just finish with some other things that Hamilton did and some of the movements into algebra, now that you're relaxed about that. And Hamilton's next idea was to try to extend to 3 dimensions and to consider number triples or triadic fancies, as he called them. So he's now looking at number triples such as ABC, and in a way now, they are triples now, but we can write them if we're trying to extend the idea of complex numbers to 3 dimensions, to triples. He wrote them as A plus BI plus CJ, where I squared is J squared is minus 1. And once again, addition was easy. Here we have where I've added 1 plus 2i plus 3j to 4 plus 5i plus 6j, and you just add the real part. You add the number of i's together, you add the number of j's together. But let's look at multiplication. All right. So if we're going to multiply those out, 1 plus 2i plus 3j multiplied by 4 plus 5i plus 6j, multiplying it by every term in the first bracket, multiplied by every term in the second bracket. And if you use the 2 relations that we have, I squared is equal to j squared is equal to minus 1, that enables us to simplify to a certain extent, doing all the terms, taking them through, using I squared equals j squared is minus 1. But what you come up with is an expression. The expression that you come up with involves the term ij. As you would expect, it has to. There's a 2i times a 6j. There's a 3j times a 5i. So there's going to be a 12 plus 15 times ij. So the question Hamilton was asking is, what is ij? And you can't do the thing which you'd be perhaps tempted to do, which is to set ij equal to 0 and therefore forget all about it, because it has a consequence, because if you set ij equal to 0, then you get 0 is ij squared, all right, which is going to be I squared times j squared, which is minus 1 times minus 1, and you find a bit of an inconsistency there, getting that 0 is equal to 1. And in fact, it became a bit of a family joke, as we can read in this letter about multiplying triples. So Hamilton wrote to one of his sons, Archibald, written many years later, shortly before his death. And it was, every morning on my coming down to breakfast, your brother William Edwin and yourself used to ask me, well, Papa, can you multiply triplets? Whereto I was always obliged to reply with a sad shake of the head, no, I can only add and subtract them. Typical breakfast conversation in many homes. All right, all his attempts failed because Hamilton wanted to construct a way to multiply triples which had similar properties to those enjoyed by the real and complex numbers. And he spent over a decade on the problem. But the strange thing is that if he suspected it could not be done, then that's easily proved. And we saw that, I'm going to show you now, there's no multiplication law for triples. The problem is what value to give to ij. Well, he wants it to be another triple. So it's going to be for some values of a, b, and c, ij is going to be another triple, so ij is going to be a plus bi plus cj for some real numbers a, b, and c. That's what he wants to get. So we take that ij equals to a, b, and c, and we're going to multiply both sides of that equation on the left by I. So ij is equal to a plus bi plus, there we are, a plus bi plus cj. Multiplying both sides by I, so you get I squared j is ia ai plus b times I squared plus c times ij. And we know what we can put in. I squared is minus 1, I squared is minus 1, and we know what ij is. Ij is a plus bi plus cj. So we feed those things into that last line as written there, and when you feed them in, and you collect the terms, I've done the collection for you to spare you. So we had this here. We started off, we said ij has to be something, a plus bi plus cj, where a, b, and c are real numbers. Multiply both sides by I. Now use the fact that I squared is minus 1, ij is a plus bi plus cj. Put them in and collect like terms, and you get 0 equals this term, plus that one here, plus this one here. But if this is equal to 0, the only way that can happen is that each of these terms in brackets has to be 0. In particular, 1 plus c squared has to be 0. But c is a real number, and for no real number is 1 plus c squared equal to 0. So it's rather strange that he spent over a decade trying to do the multiplication. And then one day he had the flash of inspiration that, that's just the conclusion. Well, coefficient is 0, which is impossible for any real number c, and I put an exclamation mark there for it. Okay. So he had the flash of inspiration that resolved the problem. 16th of October, 1643, Hamilton was walking along the Royal Canal in Dublin to a meeting of the Royal Irish Academy when he later wrote. And he is very verbose. He never uses one word when 2 or 3 might do. An undercurrent of thought was going on in my mind, which gave me at last a result, whereof it is not too much to say that I felt at once the importance. An electric circuit seemed to close, and a spark splashed forth, the herald, as I foresaw immediately, of many long years to come, of definitely directed thought and work by myself, if spared, and at all events on the part of others, if I should ever be allowed to live long enough, distinctly to communicate the discovery. I pulled out on the spot a pocketbook, which still exists, and made an entry there and then. Nor could I resist the impulse, unphilosophical as it might have been, to cut with a knife on a stone broom bridge as we passed it, the fundamental formula with the symbols I, j, and k, namely I squared equals j squared equals k squared equals ijk equals minus 1, which contains the solution to the problem. And Hamilton, I suppose in some, was a compulsive scribbler, and according to one of his sons, if there was no paper available, he would write on his fingernails, or if at breakfast, scribble on his hard-boiled egg. There must be quite some breakfast in that family. So what did he see in this flash of inspiration? Instead of triples, he added another term, k, which also satisfied k squared equals minus 1, giving him quadruples, or, as he called them, quaternions. And those were the fundamental relations of them, so let's just get a little bit of practice of looking at them. These relations imply that ij is not equal to ji, but ij is equal to minus ji, so you've lost commutativity. The order in which you multiply things matters. And let's just see how we could show that on the basis of this relationship up here. We have ijk is minus 1. We multiply on the left by I. Is that what we're doing? Oh, sorry, you multiply on the right by k. That's very good. I was just testing. I hope the people who are watching us in live streaming are also as alert. So k times k, that gives you your -1. So you get minus ij is minus k. Ij is equal to k. So k is equal to ij. Now let me start off with the same fundamental relationship, but this time I'm going to multiply on the left by j times I. So multiplying on the left by ji there and minus ji I get over here. Then the I squared here collapses out. I squared is -1, which means the j squared can be taken out as well, giving you minus k equals minus ji. So we also get that k is equal to minus ji. So ij equals k, but k equals minus ji. So we have lost in this system what we do have for the real numbers, what we do have for the complex numbers, that their multiplication is commutative. It doesn't matter what order you multiply them in. In the quaternions, that is not the case. The order of multiplication does make a difference. And this was important that he saw this and still have a consistent and a meaningful algebra. Right. And it was important in the development of abstract algebra. And here, just a little, in order, it is just stressing, really the whole point of this slide is stressing the lack of commutativity. If you write the three of them out here, ij and k, and you go round it this way clockwise, you get ij is k, as I've written down here, jk is I, ki is j. But if you multiply them going the other way, and you want ji going anti-clockwise, yes, that's right. Ji is giving to minus k, ik is minus j, and kj is minus I. All right. And he was very pleased with this. He even wrote a little poem about it, saying of how the one of time, of space the three, mighty in the chain of symbols girdled be. And although they didn't become as popular, as widespread as Hamilton wished they would be, they were important, for example, in the development of vector analysis. And I just picked one example of where they'd appeared, for example, in Gresham lectures before, one that I gave, but also very nice one here. Not that mine wasn't very nice, but this very nice one here by Chris Budd, where he, in his lecture, Mathematics Goes to the Movies, where he shows how quaternions can be used in computer graphics in the transformation of any directed line in 3 dimension to any other directed line, and I've given the link to that lecture, which is well worth looking at. So, to the last section then. We've met the reals, we've met the complex numbers, and we've met the quaternions. Are there any other similar number systems? It could be proved that there's only one more if we're prepared to abandon another arithmetical law. And they're called the octonions, and they were introduced independently by John Graves, a friend of Hamilton, and Arthur Cayley, an English mathematician. And each octonion consists of 8 terms of the form A, B, C, D, E, F, G, and H are, are real numbers, and then the I, J, K, L, M, N, and O are octonions, which satisfy, these are the simple relationships. The square of each of them is -1. And then there's a various, you know, the way I had that diagram with clockwise and anti-clockwise. There's other kind of diagrams that show how they combine with each other and what the result is. But now, they are not commutative. The order in which you multiply them makes a difference, can make a difference. But you also lose the fact the multiplication is not associative. And what does that mean? Well, normally, if we were with real numbers or complex numbers, if we have 2 expressions like this, A times B, evaluate that, take that answer and multiply by C, you would expect to get the same as if you evaluated B times C and pre-multiplied that by A. But for the octonions, it needn't be the case that those 2 things are equal, so that you lose more or less the last arithmetical property that you had. And with the octonions, we come to the end of the tale. There are no more similar number system, a result proved at the end of the 19th century. Well, just give you a reference because there's a very fine website here. David Wilkins, member of the British Society for the History of Mathematics at Trinity College Dublin, has got a very fine website containing lots of original papers by Hamilton, which was well worth having a look at, and he's gathered them all together and has made it very nice. So I'm going to stop there. Just a note here, Valerie says to remind you to hold on to your tickets, because if you don't have your tickets, you're not going to get back to see Robin, and you would not want not to do that. So thank you very much.